Now we are on chapter 3. Here there are 2 or 3 different parts, as we can call them. The broad name of the topic is called as network analysis. That means we are going to draw some kind of network diagrams, which will be very helpful in drawing a lot of conclusions. So I'll divide this chapter into broadly 3 parts. First is CPM. CPM, as the long form for CPM is critical path method. So I'll write here critical path method, that is the long form of CPM. Critical path method, CPM, critical path method. It's a network technique which will give us lot more information than what is visible. Now the second part which we'll be doing in the network analysis will be under CPM only, but we'll be calling it CPM. So A will be CPM, part B will be CPM crashing, and part C will be PERT, or what is the long form of PERT? Project evaluation, and review technique. PERT, sometimes also known as program evaluation and review technique. Both the names are prevalent. So this is part C that we'll be doing. So I'm breaking up this chapter into 3 broad parts. CPM 1, CPM crashing second, and PERT calculations the third. Now what is CPM and PERT? Both are actually quite similar in nature, but the situations in which CPM is used and situations in which PERT is used are different. Okay, fine. Now a network analysis, that this chapter is called. What is network analysis? We are going to draw some kind of diagrams, different type of diagrams which we have so far not drawn. They are called as network diagrams, and these diagrams primarily consist of only 2 parts. Okay. Now this is one question which I have written here, but it will be some time before I come to this question. I have simply written it for reference. This is one of the first problems that we'll be solving under CPM. Now see, there are basically only 2 components in a network diagram. Okay. What are the 2 components? One is called as event, and the second one is called as activity. Okay. What is an event? Event is not what we understand in day-to-day life by event. For example, we sometimes use the term like birthday event or marriage event and so on. That is not the meaning in the context of CPM. Okay. And what is an activity? Activity is what we understand as activity in day-to-day life. It is similar to the concept in CPM as well. In CPM also, what we call as an activity is what we call an activity in day-to-day life. For example, suppose this video lecture, okay, of mine. Video lecture of mine, let's say it commences at 1 p.m. Starting time of the lecture is 1 p.m. and suppose it ends at 3 p.m. Okay, it's a 2-hour lecture. Starts at 1 p.m. ends at 3 p.m. Okay. Then what is 1 p.m. and 3 p.m.? These are events. What is an event? Event is a point in time. In a day's clock, it is the clock time or the time shown in your wristwatch. For example, 12 noon, 1 p.m., 3 p.m., 11 p.m. These are all times on the watch. Okay. So this is an event. It's nothing but a time, particular moment. Okay. Now, for example, in a day's calendar, it can be hours, but in a week's calendar, it could be days. For example, I'm doing something between, let's say, Sunday to Wednesday. Okay. So Sunday is an event. Wednesday is an event. Okay. And what am I doing between Sunday to Wednesday? Let's say I'm preparing for my exam for OR. Okay. So here I can say Sunday is an event when I started studying the OR subject, and Wednesday is another event where I finished studying the OR subject. So what is Sunday and Wednesday? These are start and end times of the activity called as studying for OR. So what happens between two events is an activity. For example, when I said the lecture starts at 1 p.m. and ends at 3 p.m., 1 p.m. is a point in time, 3 p.m. is a point in time. What happens between 1 p.m. and 3 p.m. is an activity which we can call as a video lecture. So video lecture is an activity. It commences at 1 p.m., ends at 3 p.m. So what we understand therefore is 1 p.m. is an event, 3 p.m. is an event, and the name of the activity is video lecture. Okay, this is symbolically shown like this. Okay, if I was to show this video lecture in terms of the network diagram that we are going to draw, I will show it like this. Event is shown always in the form of a circle. Okay, remember, event is shown in the form of a circle, activity is shown in the form of an arrow. Okay, so this is 1 p.m. event, 3 p.m. event, and what happens between these two is an activity called as video lecture. It has got a direction, video lecture. Okay. So the video lecture, in other words, commences at 1 and ends at 3, and it can proceed only in one direction. It can start at 1 and end at 3. No video lecture or no activity can commence at 3 and end at 1. Reverse passage of time is not possible. Only forward passage of time is possible, and therefore there is always a direction on this straight line, and therefore it is called as an arrow diagram. There are all arrows. Arrow shows what? This is the forward direction. Arrow goes in this direction. It starts from here, ends here. Okay. So what are the two components therefore in a network diagram? An event, which is shown as a circle, and an arrow, which is nothing but a straight line with a direction. Okay, and straight line with a direction is called as arrow, and only two components, event and activity, or a circle and an arrow, and that's all. And that is all that is there in a network diagram. Then what else is there? Why is it so much of time consuming to learn this process? There are certain calculations associated with this. Okay. Now understood what is an activity. Activity is some physical process which consumes resources, which consumes effort. For example, when I say video lecture, on my part, it consumes my resources to explain it to you. On your part, it consumes resources on your side or efforts on your side to assimilate or understand the lecture. But what is 1 p.m. and 3 p.m.? They do not require any resources. 1 p.m. is just a point in time, and 3 p.m. is just a point in time. Now in a day's calculation, 1 p.m. and 3 p.m. is okay. But suppose you are studying the subject, let's say your examination is in the month of April, and let's say between 1st April and 15th April there are no lectures, and therefore you start your studies on 1st April and you end your studies on 15th April. Okay. So 1st April, 15th April, what are these? These are points in time. Either it is a day or a date or a year or a month or whatever it is. And what is happening between 1st April to 15th April is a thing called as study, or an activity is called as study. So I'll say it starts on 1st, ends on 15th. So the direction of the line is this way. That means this is an arrow pointing towards 15th April, and this can be called as study for semester 6. Study for semester 6, or whatever semester that you are doing. Study for semester 1, 2, 3, 4. This is the direction of the arrow. That means it will start on 1st April, end on 15th April. Reverse is not possible. You cannot start study on 15th April and end it on 1st April, because you cannot travel in the reverse direction of time. So the direction of time is always forward. This is one thing. Okay. Now activity, I have understood. Activity is something which happens between two events, and activity consumes resources. Activity requires efforts. Okay, activity requires money, it requires manpower, it requires machinery, and so on. Okay. And what are the events? Events don't require anything. Events do what? Events just mark the beginning of an activity and end of an activity. For example, suppose there is a reputed builder in your city and he wants to construct a residential tower. What does he do? Let's say on 1st April of the year, he gets possession of the land with the titles being transferred in his name, etc. Legally, the land is his own. And he is confident that on next April or before 31st March in the next year, he'll be able to give out possession of the flats to the buyers. So I can say that this whole project starts on 1st April and ends next year on 31st March. So the duration of the project is 12 months. But what are the things which are happening in these 12 months? Several things are happening in these 12 months. Financer is going to finance the project. Individual buyers are going to approach their banks for loans. The construction work is going on. The builder is going to get approvals for from the municipality for various drawings and designs and so on. The fire department is going to approve everything. Then the construction work will start right from the plinth level up to the top floor, whatever floor he is going to. Slabs will be put one by one and so on. So there are innumerable activities in respect of any project. Even for that matter, if you are setting up a small scale unit for manufacture of some product, this will require several individual activities to be completed when you can say that, okay, I have completed my project and now I am ready for commercial production. The day you are ready for commercial production, your project implementation is over. And how to monitor that project implementation? Using the technique called as CPM or critical path method. What is the purpose of this technique? The purpose of the technique is like this, that once you draw the network diagram, you will come to know which are the most important activities in the project, which activities I can afford to delay, which activities I can never delay if I want to complete the project on time, 31st March next year, which activities I cannot delay, which activities I can afford to delay. There will be some activities which you will be able to find out that, okay, even if this activity instead of 1 month, it takes 1.5 months, it doesn't really affect the final implementation of the project, or the projects can still be completed on 31st March. Then how much time is available excess with any activity wherein I can delay that activity. Okay, all these questions will be answered the moment we draw the network diagram. And what does the network diagram comprise of? The network diagram comprises of only these two things: an event and an activity indicated by an arrow. Okay, fine. So we have understood the distinction between event and activity. Event does not require resource consumption. Activities cannot be completed without resource consumption. Events mark either the beginning of an activity or events mark the end of an activity. When the activity starts, it is a start event for the activity, and when the activity ends, it is the end event for the activity. So I have understood the distinction between event and activity. Really speaking, there are only these two components in the drawing of network: event and activity, event and activity. Now the complications come because there are several events, there are several activities in the project. As I said, for constructing a housing complex, there are several activities, or setting up an industrial unit of your own, there are several individual activities, and therefore the calculations become in fact very important, because there are several of events. Now see, typically how many events will be doing? We may have about 8 to 10 events, about 8 to 10 activities. We are going to the very simple level of network diagrams, not highly complicated, and therefore our networks will not be too complex. We may occasionally have a complex network which we'll come to, but the calculations as they appear are not actually really difficult. Actually, the calculations are quite simple. Okay, it is nothing compared to what you did in the case of transportation problem, or for that matter simplex algorithm. The calculations are extremely easy. Okay, so how do we go about it? Now, having understood what is an activity, I'll distinguish activities into two types. Activities can be sequential or activities can be parallel. What are sequential and parallel activities? Let me explain. Okay, suppose you are working at a distance of about 10 kilometers from your residence, and every day it is your practice to take a train and go to the place of work. Okay. So what is the time required for this 10 kilometers? Depending on the condition, if you take a train, it will take lesser time. If you take a road, it will take a little longer time. In Mumbai, there is always traffic. As a result, suppose 1 hour is what is provided for traveling. May not be a distance of 10 kilometers, but maybe a distance of 20 kilometers. You can easily provide 1 hour, whichever way you go. That is the minimum. Okay. Now what happens? Let's say you board a train at 8 o'clock. At your residence, near your residence, you board a train at 8 o'clock and you reach the destination at 9 o'clock. That means this 1 hour is the traveling time. Now, do you sit idle in this traveling time? No. There are several things to do. You may read the current newspaper in this 1 hour. Once you have boarded the train or the mode of transport, whichever you have chosen, whether it is bus or your taxi or your train, you know that you have 1 hour at your disposal. What do you do in this 1 hour? You can do several things. And some of the typical things are what? Read a newspaper, check your messages on the mobile, check some websites, do some shopping. These are all the things which you can do while you are traveling. But the starting point and the end point of traveling is already well defined. You are going to start your journey at 8 o'clock. You are ending your journey at 9 o'clock. But this 1 hour you can utilize for several things of which I gave examples. So the several things which you are doing simultaneous with the process of traveling are called as parallel activities. They consume the same amount of time. For example, it could be travel, it could be reading newspaper, it could be sending mail or messages, it could even be hearing some music. You are going to utilize this time 8 to 9 in several other ways, and some of these things are mentioned here. So parallel activities are those which can be done simultaneous with other activities. For example, 8 to 9 you are traveling and you are doing all these things parallel to or simultaneously along with traveling, whether it is sending a mail, doing some work on your laptop and so on. So these are called as parallel activities. They don't depend on each other. They consume the same amount of time. That is important. Now, sequential activities is something which is different than parallel activities. Now, what is a sequential activity? In sequential activity, as the name suggests, a certain sequence has to be followed. What are the sequence? For example, suppose we are traveling on the highway and suppose one of our tires gets punctured. What is the process? You have the extra tire with you, you have the stepney with you, and you are able to change the tire yourself. So what do? You go on the side of the road, stop the car on the side of the road, take out the flat tire, take out the nuts, take out the flat tire, put the new tire or a replacement tire over there, fix the nuts, and then you are going. And at the next opportunity, you will get the punctured tire repaired from a shop. Okay. So what happens in this process? You stop, old tire removed, new tire fixed, and then you start. You stopped, you removed the old tire, you fixed the new tire, and then you are ready to start. Fine. Can you see that this sequence has to be followed in this direction? You must first stop, then first change the old tire, then put the new tire, only then you can start. You cannot change the order of these activities in any way. For example, it is not possible to fix a new tire before removing the old tire. So I can't say I'll fix the new tire and then remove the old tire. How will you fix the new tire without removing the old tire? So removing the old tire always comes prior to fixing the new tire. So these activities are called as sequential. Okay, they must follow a certain sequence. This happens after this, this happens after this, and so on. So there are activities which are parallel, which can happen at the same time, and there are activities which must be sequential. Sequential in the sense they must follow a certain logical sequence. For example, when I'm constructing the building, I don't go to the last slab. I start the slabs from ground floor onwards and then go at the top and then put the last slab. I cannot reverse the process. Okay. But when you are painting the building, for example, all the physical construction of the work is over and you are painting the building, nobody is going to tell you that you don't do the 20th floor first and then go to the ground floor, or go to the ground floor, then do 15th floor, then go to 30th floor and so on. Any sequence you can follow because the building is ready. The painting does not require to be in any particular sequence as to 1, 2, 3, 4. But the slabs have to follow the sequence 1, 2, 3, 4. So slab laying is sequential. Painting is not sequential. Painting can even be parallel. Suppose there are two painters, they can do 2 floors at the same time. So it can happen at the same time. 2 teams are doing the work, so it can happen at the same time. So this way we distinguish between sequential activities. So what are sequential activities? Sequential activities therefore are those which depend on some other activities getting completed. For example, fixing a new tire depends on removing the old tire. And removing the old tire in turn depends on stopping the car. And starting the car again depends on the new tire getting fixed. Okay. So this is the distinction between sequential and parallel activities. Sequential activities must follow a certain logical sequence. Parallel activities are those which can be done at the same time. See, for example, when you are setting up an industrial project, you are physical construction of the work is already on. Now you are required to obtain certain approvals. Okay. Now some approvals are required before the residents start shifting in. So it can take time. Simultaneous with the work, the approval process can go on. For example, once the building is completed, I can go to the fire department, I can go to the municipality for occupation certificate, and suppose these two things are independent, they can happen at the same time. Or an industrial project, you want to have a sales tax registration or a GST registration, and you need to have the bank's completion certificate for the project. These two things can happen at the same time. One does not depend on the other. So that way, sequential activities and parallel activities help us to understand what should be the logical sequence and how much time will this project take. It all depends on which activities are necessarily sequential and which activities are necessarily parallel. So we have explained at little length what is the difference between event and activity. Event is marking the end or beginning of an activity. An activity is a physical process which consumes resources. Within activity, we have parallel activities and sequential activities. Later on, we will also introduce a term called as dummy activities, but as the name suggests, these are not real activities, these are dummy activities. Okay. Now look at this table. This table gives us some relationship between the various activities. The names of activities involved in this project are going from A to F. That means there are 6 different activities in this project: A, B, C, D, E, F. What are A, B, C, D, F? In real life, they may stand for some real activity. For example, A, activity A may be acquire land for the project. Okay. Activity B may be get approval from the bank for loan, etc. We are not interested at this stage what A and B stand for. We know that there are 6 activities in this project. What does it mean? There are 6 arrows in this network diagram. There are going to be, because there are 6 activities, there will be minimum 6 arrows in this network diagram. You know the arrow diagram now. Arrow diagram is what? Arrow diagram will commence at an event, end at an event. Okay. And there will be an arrow to join the two. And the time passage is only forward, not backward. Having said that, now let me understand what are the activities here. There are 6 activities of the project. And what are the next column? Predecessor activity. By predecessor activity, what we understand is like this. Activity A does not depend on anything because there is no predecessor activity or pre-required activity. So far as activity A is concerned, there is no prerequisite. For activity B also, there is no prerequisite. That means no other activity is required to be completed. Okay. So A and B are nothing but beginning of the project because they do not require, against their name there is a dash. That dash means activity A and B do not require any other activity to be completed. Okay. Then I'll come to C. C requires that A should be completed. Okay. What does it mean? Remember, the activity duration for activity C is 3 days. Last column is days. Activity D depends on activity A to be completed. This is something like putting the new tire only after removing the old tire. Okay. Now activity C, since it cannot be completed and activity C requires A to be completed, activity C cannot even start unless and until activity A is completed in all respects. So activity C presupposes that activity A is completed in all respects. Similar situation in respect of activity D and E. Both these activities require that activity B should be completed before I undertake activity D. Even E requires that activity B should be completed before I undertake activity E. F, little more different. F requires that both C and D should be complete. Activity F requires that both C and D should be complete. Now see, activity F requires that C and D should be complete, and C requires that A should be complete. What about D? D requires that B should be complete. Okay, fine. So activity F is actually, can you see that after F there will be nothing in the project? Now look at this network like this. Are there any activities which don't depend on anything? Obviously the first two activities, against their name there is a dash, A dash, B dash. That means activity A and B do not depend on anything. These are invariably the start activities of the project, and start activities of the project will always have a dash against their name. That means the moment I announce that I am doing this project indicated by this information, activities A and B can start immediately, and the time at which they start the project, for that matter the project starts, I call it time 0. And since the durations in the last column are in terms of number of days, now it could be number of days, or it could be weeks, or it could be months, and so on. Okay, now we are sticking to number of days because this project is about number of days. The start time of the project is day 0, and on day 0 A can start as well as B can start. Okay, because A and B do not depend on anything. Okay, now are there any activities in this first column A, B, C, D, E, F on which nothing depends? Activities A, B, C, D, E, F are 6 activities of the project. A and B do not depend on anything. Are there any activities here on which nothing depends? Can you see? This information will be available if I scan the second column. And which are the activities missing in the second column? A is there, B is there, C is there, D is there in the second column. The names E and F do not feature in the second column. That means nothing depends on activity E and F, which also means that activity E and F must be end of the project. What we understand therefore is when activity E and F are complete, the project is complete, because thereafter there is nothing. Nothing is going to depend on E and F. Therefore E and F, the activities which are missing from the second column, are the end activities, and activities A and B are the first activities of the project because they do not depend on anything. Okay. So the moment we see this kind of relationship, two questions must come to my mind. Which are the first activities? Which are these? A and B, and which are the last or end activities? Those activities which do not feature in the second column under predecessor activity are the end activities or last activities, and over here for this network it is E and F. So there is nothing before A and B, and there is nothing after E and F. In other words, whatever we have A, B, C, D, E, F, there is nothing before A and B, nothing after E and F. So my network will comprise from left to right. It is a standard practice to draw the network from left to right. Okay, because the forward direction of time is from left to right. How do we normally process the human eye? How does it process the information? As I said, human eye processes the information from top to bottom and left to right. If I give you something to read, how do you read it? We start at the top and at the top we start from left and go to the right. So human eye is trained to process the information from left to right and top to bottom, and that is exactly how we'll draw the network diagram from top to bottom and left to right. Okay, done. Now I'm starting drawing this network diagram. Remember, network diagram is what? Only two things: events, activities. Okay, so there are some rules regarding drawing this network diagram. Those rules will be available in the note which is there before you. Both the soft copy and hard copy will be given to you. It has already been with you actually. So if you read the beginning part of this chapter 3, all the rules of drawing the network diagram have been stated there, but without you having to read them, I'll explain them right now here itself. First thing is identify the first activities of the project, done A and B. I just make a mental note of this. Activities A and B, the first activities of the project. So since they are the first activities of the project, I will start drawing the network diagram from activities A and B. One of the rules for drawing the network diagram is that there should be one start event and there should be one end event. Okay. In other words, I cannot show like this. This is activity A, this is one event, activity A goes out like this. This is another event, activity goes out like this. This is wrong. Because remember, we are at the start of the network. Start of the network must be a single event. Okay. So, I'll start drawing the network. See, it is always a good practice. However expert you may be, you must start drawing a rough diagram first, because many times you will find, maybe not in this problem, in some other problem, you have to make changes as we go along in the directions of the arrows, maybe the placement of arrows, how the network is going to look. Many times we have to make changes. Therefore, we always draw a rough diagram. So I am drawing a rough diagram right now. As I said, there is only one start event, so I am drawing a event. Event is when the project starts. This is called as time 0. Okay, the calculations we are going to go a little later, and we'll complete the calculations of how long will this project take and so on also. But let me presently draw only the network diagram. As I said, A and B can start simultaneously, so I give them alphabetical names such as A and B, and the circle which I have drawn is the start event of the project. Since activities A and B are the first activities, both of them can start immediately. So I have drawn one arrow A and drawn another arrow B. Now remember, every activity must start at a circle and end at another circle. So in other words, at the end of these arrows, there are going to be some more circles. So what has happened about activity? It has started at this event, it has ended at this event. Similarly, activity B, it has started at this event, ended at this event. Okay, done. Activities A and B, the simplest thing which we have drawn is activities A and B. So let us put a tick mark, small tick mark against their names. Okay, A and B have been drawn by me. Now go to the next one, C. Activity C I am going to draw. But activity C depends on completion of activity A, and therefore C cannot even start unless activity A is complete. The new tire cannot be fixed unless the old tire has been removed. Therefore, activity C will start only when activity A is complete, and activity A is getting completed at this event, and therefore C can start now. Of course, I am going to end C also in another circle little later. Okay, so I have drawn activity C. Just understand the process of drawing the network diagram. I am consciously taking up a very simple network diagram right now. Maybe after 3 questions, the diagrams are not going to be as simple. They are going to be little more complicated. Now, C activity depends on A, so I have drawn C at the end of A. When can C start? At this event. What is this event? This event marks the end of activity A. So unless A ends, C cannot start. So the end event of activity A is nothing but the start event of activity C. Okay, done. A, B, C drawn. Then next I draw is B. D. Now D depends on completion of B. Similar situation, just as C depended on the completion of A, D depends on the completion of B. So I draw here D. This is start event for activity D. This is end event for activity B. Okay. D is drawn. Then E also depends on B. Okay. Activity E also depends on activity B. That means this activity B controls two activities. B controls D, B controls E. Therefore, E also starts at the same time as completion of B is achieved. When is completion of B achieved? Completion of B is achieved here. As soon as B completion is achieved, D can start, E can start, and therefore both of them have started. Okay. Done. So I have drawn E. Now I come to F. Activity F is such that it depends on completion of two activities, C and D. Now where is C and D? C and D I have shown separately, and since activity F depends on completion of C and D, I will merge C and D into one event. That event will be what? That event will be such, suppose I draw an event here. This event marks completion of C, and therefore I will draw revise C little bit. I'll say that this is my C. This event will also mark completion of D, and therefore I will say this is my activity D. Why am I joining C and D into one event? Because something depends jointly on completion of C and D. And now my activity F can start, and activity F can start on completion of C and D. When will this event be reached in time? C ends here, D ends here. So unless and until C and D both end, this event will not happen in time. For example, this may be day 12 or day 15, whatever it is. Calculations will do separately. On day 15, maybe C and D are both complete. And only then, when both the activities are complete, I can commence activity F. Because F depends on completion of both C and D. So what is this event therefore? This event is an intermediate event which marks the end of activity C and D, and it marks the beginning of activity F. Okay, done. Now we had made an observation. We had said that activities A and B are the first activities of the project, and we had also marked at the same time that activities E and F are the end activities of the project, and end activities must merge into an event, a unique event, and therefore finally what I feel is we must merge activities E and F. So I'll now merge activities E and F instead of drawing them separately like this. So I'll say this is my E and it ends at this event, and this is my F, and since E and F are the end activities, the end of the project must be a unique event. This is the end of the project, which is a unique event, and after that there is nothing in the network diagram because E and F are the end activities of the project. So thus what we have said is, we have drawn, can you see that there are 6 activities in the network diagram here given in the first column, and these 6 activities are represented by 1, 2, 3, 4, 5, 6 arrows, and the network diagram is going to look like this to me. Okay, so this is the way to draw the network diagram. This was a simple exercise. We'll have complicated relationships, in which case we'll have to make changes in drawing the network. Here also, if you see, I had drawn C and D separately, then I decided to merge them. Then I had drawn E and F separately, I decided to merge them. So these are the changes as we went ahead. We had to make these changes. So the final network diagram is ready. Now there are 6 activities, because in the given problem there are 6 activities, therefore there are 6 arrows here. And how many event circles are there? Event circles you cannot make out by looking at the table. Event circles will be known only when successfully drawing the network diagram correctly. Now see, 1, 2, 3, 4, 5. I required 5 event circles. That means there are 5 events in this network diagram, and there are 6 activities in this network diagram. And because of the relationship which is shown as per this, the network is going to look like this. Okay. Now what are events? Events are circles. What is the how to tabulate the events? Events have numbers. Activities have alphabetical names such as A, B, C, D, E, F. These are alphabetical names. So similarly, just as arrows have alphabetical names, events have numbers. So we'll be using numerals inside the circles. So as we can see from here, there are 5 events and therefore there are 5 circles. So they'll be numbered as 1, 2, 3, 4, 5. Okay, fine. So we'll have 5 events, 6 activities, the network diagram which looks like this. Now see, if I change the relationship table slightly, the diagram will look totally different. Okay, we'll see that. Now I want to do some calculations for this and I want to understand how to estimate when this project will be completed. Okay. Now there is one simple way of estimating when the project is completed. For that purpose, let me write down what are the durations of activities on the respective arrows. For example, as per the table, activity A is going to take 6 days. So I'll write here 6. Activity B, 4 days. Activity C, 3 days. Activity D, 8 days. Activity E, 14 days, and activity F, 8 days. These are the durations of individual activities in terms of number of days, because the given table is of number of days. Done. Now what next? I need to calculate when this project will be complete. Okay. Now imagine, when will this activity be starting? This activity starts at this event. When will it start? Only when this event is reached. When will this event be reached? Only when both the activities ending here are complete. Okay, that means activity D has to be completed, activity C has to be completed. When will this event be reached? Only when this activity is complete. When will this event be reached? Only when this activity is complete. Now see, there are here totally 3 types of events. This is a start event where arrows are only starting. This is an end event where arrows are only ending. See, no new arrows are starting from here and no arrows are ending here. No arrows ending here over here. Arrows are only starting from here. Here arrows are only ending. No new arrows are starting. What about these 3 events? These 3 events are such that arrows are ending here and arrows are starting here. Okay, so these are intermediate events. This is the first event, that is the last event, and other events are intermediate events. So here arrows will end, arrows will start. At the first event, arrows will not end, arrows will only start. And at the last event, arrows will only end, arrows will not start. So which is the first event of this network? This is the first event. And which is the last event? This is the last event. So if the numbers are going to be 1 to 5, I can visualize only one thing, that this is going to be event number 1 and this is going to be event number 5. That's all that I know. I do not know about 2, 3 and 4. Okay. I do not know whether this is 2 or this is 2. I do not know right now. We'll find out a way how to number the events. How to number the event? There is a specific rule for that which we will follow. But before that, I have drawn the network diagram, and from this network diagram, I understand a few things. Before coming to this network diagram, let me give an hypothetical example. Suppose we have a meeting of 3 groups of people at point B. This is, or let me say, I will not confuse it with the names of activities. So let me say at point T point, there is a meeting, and the names of the teams which are going to go for the meeting are, let's say, J, K and L. These are names of the teams which are traveling from P point to T point. P to T, they have to start their journey at P, they have to end their journey at T, and they have to meet at place called as T. Okay. The names of the teams are J, K, L. J is supposed to start from this point by train and reach point T. K is supposed to start, let's say, by highway, travel on the highway and reach point T. And team L is supposed to go by a city road and reach point T. Okay. City is a populated city like Pune or Mumbai, and therefore city travel is a time consuming affair, but within that highway will be a little better than the city road. All the teams start at the same time from point P. They are required to go to point T, and thereafter they are undertaking some other project. First, their first objective is to reach point T. Okay. Now, team called as J goes by train. So in all probabilities, they will be the fastest to reach. Let's say they take 20 minutes to reach here. They take a train. In 20 minutes, they reach point T. The next team which is going by highway takes, because the traffic and all that on the road, it takes 35 minutes to reach point T. And the team L, which is supposed to go by city road, it takes 45 minutes to reach point T. Any subsequent activity which they are going to do at point T, we are not concerned with that, but that can start. The condition is that activity can start, or that project itself can start only when all the three teams J, K and L reach point T. Okay. They are starting at the same time from point P. Their all destination is point T. One team takes 20 minutes, one team takes 35 minutes, and the last team takes 45 minutes. So what do you think? When can the project start? At point T, their subsequent activities, when can they start? The condition is all the three teams must reach before the project can start. Can you see that the one who is going by the longest time road, that is city road, will decide when the meeting at point T or the subsequent activity at point T can start, but they are taking the longest time to reach. What will happen in respect of team J? They are going to reach in 20 minutes itself out of total 45 minutes, which when all the teams will reach, they are going to take only 20 minutes. So what happens? They have 45 minus 20 or 25 minutes extra available with them. So they can do anything which they like within these 25 minutes. They can get down in between from the train, they can have a cup of tea, again chat, make some phone calls, and yet reach the destination before 45 minutes, because they have lot of spare time to the extent of 25 minutes. The second team K, which is going by highway, has some spare time to the extent of 10 minutes only. So they still have time for a cup of tea. They can still reach in time. But can you see that the team going by city road will not have any spare time available with them? So if the J team is delayed a little bit, or the K team is delayed a little bit, it does not matter. But if the L team is delayed even by 1 minute, the meeting will start 1 minute late at point T. So in other words, the team which takes the longest time will decide when the project can be completed. Now what is the project? Reaching point T. This is the project. Team J will have spare time. Team K will have spare time. Team L does not have a single spare time of a minute also, and therefore as soon as team L reaches, the project starts there, and therefore the team taking the longest time to reach will decide when the project can start at the earliest. Precisely the same thing happens in respect of the CPM network. The team which takes the longest time will decide when the project can be complete. So let's come back to this concept of the network diagram which we have drawn. Here is a network diagram comprising of 6 activities and 5 events, and I am trying to find out when this project will be complete. The situation is exactly similar to the hypothetical example which I gave you. We have to find what are the different ways and roads from the start of the project to the end of the project. Suppose these are imaginary roads. You can travel only in the direction of the arrow on the road. You cannot travel back and forth. You can only travel in the forward direction of the arrow. You can all start from here and you have to end your journey over here. Which are the different ways in which I can reach the end event? If I start from here, I can go via ACF. What is the other way of reaching this event? BE. Any more way? BDF. See, they are all what? They are all starting from here, ending here. That is the criteria. Any other way? No, I don't think there is any other way. ACF, BDF and BE. These are the three ways of reaching the end event. And how long does it take? Now, for example, ACF, look at the ACF. This is an imaginary road going from the first event to the last event. This 3 days time will start only after completion of 6 days, because this activity cannot start unless this is complete. This activity taking 8 days cannot start unless this activity is complete. So the duration of this path ACF is 6 plus 3, 9, 9 plus 8, 17. Okay. Next, BE. BE. One team goes via this road. 4 plus 14, 18. So path BE is 18 days long. Path ACF is 17 days long. And what about the remaining path? BDF. Let's calculate. BDF. 4 plus 8 plus 8, that's 20. The longest time. When therefore do you think that the project will be complete? Situation is exactly similar to the hypothetical example. JKL teams. L team taking the longest time will decide when the meeting can start at point T. And similarly therefore here the team taking the longest time is taking 20 days, and that route which they are taking is BDF. Therefore BDF being the longest route, this is the duration of the project. Duration of the project is therefore, what is the duration of the project? Now we understand. Duration of the project is therefore the duration of the longest path from the first event to the last event. Out of the longest path from the first event to the last event, it is BDF. You start from the first event, start event. You have to reach the end event. If you go via BDF, that will take the longest time. And unless all these three activities BDF are complete, the project can no way be complete. And therefore 20 days is the duration of this project, when all the activities of the project can be completed. But what happens to this path ACF? Can you see that it has got 3 spare days, 20 and 17? Okay, this is our teams, team J and team L. And here this path is taking 18 days. That means there is some spare time of 2 days. Here there is a spare time of 3 days. Means in one of the paths there is a flexibility of 3 days totally. And in one of the other paths there is a flexibility of 2 days totally. As a result, these paths are not critical. The critical path is the longest path, and the longest path over here is taking 20 days, and therefore the duration of this project is 20 days. That is what we have found out. Okay. Now this is not a scientific way of finding. This is correct. This is correct. But what happens if when there are number of events and number of activities, it is sometimes very difficult to find out all the paths going from the first to the last event. For example, a little more complicated network, and there may be some other routes of going via some other activities. We may miss out on them. And if we miss out on those paths, it is possible that one of those missed out paths may be the longest path. So this is not a scientific way of finding out. For a simple network like this, yes, the problems which we are going to face in our studies, yes, we can probably directly find out the longest path by jotting down all the paths. But here, the scientific way is doing the calculations at each event. When will this event be completed at the earliest? When can this event be completed at the latest? And so on. Once we do those calculations, we'll be able to say with authenticity that yes, now this event has some flexibility, or this activity has some float, or this event has some slack. Say I'm already talking about some new terms. I have used the new terms today: event, activity, critical activity, non-critical activity, parallel activity, sequential activity, start event, end event, start event, end event, and intermediate event. These are the new terms which I have used. Now I have introduced the term called as slack and float. What is float? Float is a measure of flexibility for an activity, and slack is a measure of flexibility for an event. Remember, slack is associated with an event, float is associated with an activity. As you read along the note, you will find out this at more detail. But before that, I want to draw the final diagram for the project. There are two objectives in drawing the final diagram. This diagram has been correct, no doubt. But do you realize we had to make several changes in drawing this diagram? We had to rub out, we had to merge, we had to segregate the activities and so on. So I'll draw the now final diagram, which will look like this. I'm going to place some calculations inside the circle. So I'm drawing a little bigger event circles than what we have drawn here. These are my 3 events. This is another event, and this is another event. Totally 5 events are required. So I'm drawing here 5 events. Okay. Now how are the activities connected? If I call this A, this is my B, this is my C, this is D, this is E, and this is F. Okay. Network diagram drawn. I would have liked to place this circle over here, but this diagram is coming in between, so I'll do that after removing the diagram. Now see, there are 5 event circles which I have drawn. The event circles are always drawn little bigger so that we can write some calculations inside the event circles. Okay. Now first thing is to write down the duration of the individual activities on the respective arrows. For example, activity A is 6, B is 4, C is 3, D is 8, E is 14, and F is 8. These are the durations or lengths of the respective arrows. Remember, the number and the length of the arrow does not have to be proportional. For example, this is a small arrow, still the duration is 14, and this is a big arrow, the duration is only 8. There is no such thing that the length of the arrow will have to be proportional to the duration of the activity. No, there is no such thing. So even a small arrow could be 25 days. Okay, fine. So I have drawn the network diagram. I'll revise it a little bit to make it look better. I have drawn the final network diagram as well. Now I'm going to break up each event circle into 3 parts. It is done like this. Firstly, break up the event circle into 2 vertical parts, and the right side part you can break up into 2 parts again. So 2 quarter circles, 1 quarter circle, 1 quarter circle. This is semicircle. So now you will find the same thing in some of the books. You will find this way. The semicircle is like this, and the quarter circles are like this. They make it horizontally, we make it vertically. It does not matter. Sometimes we can make it vertically, sometimes we can make it horizontally. It really doesn't matter. What we write inside is important. Now all the event circles are broken up into 3 parts. So on the left hand side semicircle over here, since there are 5 events, I am going to write the event numbers, and the event numbers are going to be 1 to 5 because there are 5 events. Are you getting a feel which is event number 1 and which is event number 5? Yes, the first event is event number 1 and the last event is event number 5. That means this is event number 1, this is event number 5. Okay. So I can easily number event number 1 and event number 5, but how to number the remaining 3 events 2, 3, 4? There is a certain logic in that. Now see, it is like this. An activity, for example, here, you know, and let me first number the event, then I'll show you. Now, firstly, in the rough diagram and the fair diagram, find out which is the start event. Which is the start event? Where no arrows are ending is the start event. Okay, For example, this is the start event here, this is the start event here. Okay, give it number 1. Start event is number 1, both in the rough and fair diagram. Give it number 1. Done. Now see what this process that I am using for numbering the events is called as Fulkerson's rule. Fulkerson's rule. This was the person who is responsible for discovering this rule or making this rule, and therefore we'll call it Fulkerson's rule. And remember, whether mentioned or not, when you are saying number the events, you have to use Fulkerson's rule. There is no other rule such as Fulkerson's or somebody else's rule. There is no such other method. There is only Fulkerson's rule. Okay. So Fulkerson's rule is what I am using. The objective is to number the events from 1 to 5. What does the rule say? Identify the first event. Have we identified the first event? Easy to identify. This is number 1. Give it number 1 in the rough diagram and the fair diagram. Okay, done. Now look at the rough diagram. Which events have been numbered so far? Only one event has been numbered so far. And what is that event number? It is event number 1. So delete that event from the rough diagram. See, this is the rough diagram. One event has been numbered. Delete this event from the rough diagram along with arrows starting from that event. Event number 1 is numbered. Which are the arrows starting from this event? A and B are the arrows starting from this event. Delete event number 1 and 2 arrows starting from event number 1. Let me do this. Arrow starting from event number 1. Arrow starting from event number 1. Deleted. Now look at the residual network in the rough diagram. Are there any events in this new network where no arrows are ending? Are there any events? Can you see this event? No arrow is ending here. Can you see this event? No arrow is ending here. Because the arrows ending there have been deleted by us only. Okay. So these are 2 new events available for numbering. Which events can be numbered? Where no arrow is ending. And since here no arrow is ending, here no arrow is ending, we can now number them with the next 2 numbers. Okay. So which number has been already allotted? Event number 1 is allotted. So obviously next 2 numbers which we can use now are 2 and 3. So I make this 2 and this 3. So this is event number 2. This is event number 3. Usually I follow a practice that the upper number lying in this north side, I number first and then the lower number. Okay. Having said that, this is event number 2, this is event number 3. And what is event number 2? Actually, beginning of activity C is event number 2. Beginning of activity C is event number 2. And beginning of activities D and E is event number 3. Beginning of activities D and E is event number 3. Okay. Done. Now which events have been numbered so far? 1, 2 and 3. So what do we do? Delete the events which are already numbered. 1 has been already deleted. Delete event number 2 with arrow starting from that. Delete event number 3 along with arrow starting from that. So I am deleting event number 2 with arrow starting from event number 2. Delete event number 3 already numbered. So I am deleting it. So all the events which have been numbered have been deleted along with arrows starting from that events. Now identify the event where no arrows are ending. There is only one event where no arrows are ending, and it is this event where no arrows are ending. And what is this event? Therefore the next number is to be given to this. 1, 2, 3 the numbers are allotted. So this is obviously therefore 4. And what is 4? Beginning of activity F is 4. Beginning of activity F is 4. And this is 5. 5 we knew already. Correct? So I am making the diagram look little better because I was short of space here. So I am moving this event little bit to the right for better looks. Okay. Okay. So I have drawn the network diagram. What I have done so far, I have drawn the network diagram. I have written down the duration on the respective arrows. Then I have numbered the events using what? Using Fulkerson's rule. I have numbered the events, and now my network is ready for calculation. Okay. So we have completed the numbering of events using what is known as Fulkerson's rule. We have not completed the calculations of this network. Now see what we are going to write inside this circle. Let me explain. We have drawn the circles like this, and we have made three parts of the circle. One semicircle on the left hand side. Here what I am going to write is event number. Event number, which we have already written. As you can see, 1 to 5, we have already written the event numbers in this diagram. Okay. Now next, there are two quarter circles. Here we are going to write the earliest time for event I. What is I? I is here. This is event number. For example, I is 5 here, I is 4 here. That is event number. This is earliest time for event I. That means here it will be earliest time for event 5, earliest time for event 4, and so on. And this is what? Correspondingly, this is latest time for event I. So EI, LI. These are the three numbers which are going to come inside the circle. So it is going to look like this. Finally, when I complete the diagram, it will be I here, EI here, LI here. I is event number, E for early, earliest time for event I, L for latest time for event I. That is the notation that we are using. This is across all the books. Most of the time the notation is same. In some books you will find it like this. Here they write like this: I here, EI here, LI here. So once you open the book, you will come to know which notation they are using. I am conversant with using this notation. We can use sometimes this, depending on the problem. Okay. Now I, EI, LI. What are these? Event number, earliest time for the event, latest time for the event. This is the nomenclature that we'll use, and we'll now complete this network diagram, because what is missing is EI, LI is missing. At each event number, what is the earliest time and what is the latest time is yet to be written. Okay. So we are going to calculate this earliest and latest time using a certain process. This process is known as forward pass and backward pass. Forward pass and backward pass. What is forward in the word forward pass? We go from event number 1, we start with event number 1 and go to the last event. For example, in this particular case, it will be 1, 2, 3, 4, 5. Why 5? Because 5 is the last event. If it was 10, we would have gone up to 10. So forward pass will be doing the calculations starting from event number 1 and sequentially going up to the last event. And in backward pass, as the name suggests, we'll be doing the calculation from the last event, 5, 4, 3, 2, 1. This starts at 5 because here there are only 5 events. In a network where there are 10 events, it will start at 10 and it will go as 10, 9, 8, etc. up to 1. Okay. What is the objective of forward pass? The objective of forward pass process, see, this is a twin process. Twin process means a process which is broken up into two parts. The purpose of forward pass is to find the earliest time for each event. Find the earliest time for each event, and this is conversely find the latest time for each event. So once the twin process is done, forward pass comes first. we'll do the forward pass calculations. From 1 to 5 we'll go, and when we reach 5 we'll immediately start the process of backward pass. In the process of forward pass, we'll find the earliest time for an event. Where do we write the earliest time for an event? At the top quarter circle. And the backward pass will give us the latest time for an event. That means this time for an event. Okay. Now I'll commence the forward pass. Remember, the project starts at event number 1. Project stops or ends at event number 5. So how do we proceed? The time at which the project starts is called as time 0. So I say this is time 0. In other words, whenever we find event number 1, the earliest time for event number 1 is always taken as 0. Because whatever time the project starts, we call it time 0. And from time 0 onwards, we start calculating what is the project duration or project time. Okay. As the name suggested, forward pass is the process of going from event number 1 to event number 5. And in the process of going from event number 1 to event number 5, what I'll be finding out is the earliest time for each event. So forward pass, I have written the earliest time for event 1. Then I go to event number 2. Okay. In the event number 2, when I go to event number 2, I ask a question here. Which activities end here? And here I ask a question in the backward pass correspondingly. Which activities start from here? This is the question. I'll stop at each and every event. 1, 2, 3, 4, 5. I'll keep on asking these questions. When I go in the forward pass, my question to be asked is which activities end here. In the backward pass, my question will be which activities can start from here. Okay. Now, forward pass, I'm going from event number 1. Event number 1, no calculation is required. We always start with a 0. Now, I go to event number 2. Okay. Event number 2, I am in the process of forward pass. I have completed 1. I am going to 2. My question is, which activities end here? Can you see the network diagram? Which activities end at event number 2? Only activity ends at event number 2, that is A. Activity A, therefore, ends at event number 2. Now see, activity A. Alphabetical name is given as activity A. We have given these alphabetical names, or alphabetical names are usually given in the relationship table. Activity A, can you see that it can also be called as activity 1, 2? Why? Because activity A starts at 1, ends at 2. That means activity A, whether I write activity A or I call it activity 1, 2, it is the same thing. Okay. So 1 is an alphabetical name which is given as per the question that is there before us, or it is the pair of events which it joins, and the event where it ends 2 must be higher than 1. For example, if you see 3, 4 starts at 3, ends at 4. This is 3, 5 starts at 3, ends at 5. Okay. The end event will always be higher in value than the start event. Okay, and to ensure that this happens, we have used what is known as Fulkerson's rule. Fulkerson's rule will ensure that each and every activity, all the 6 activities in this table, will start at a lower number event and end at a higher numbered event. So, having said that, I have come to event number 2. My objective is to find out the earliest time for event number 2. I am trying to find the earliest time for event number 2. So I ask a question, which activities end here? The answer which I get is activity A ends here. Okay. Activity A, what time it can start? When the project starts. Activity A can start at time 0. It takes 6 days for completion because the duration of activity A is 6 days. So when will it be over at the earliest? 0 plus 6. That is 6. Okay. Now, I have completed the calculation at event number 2. I go to event number 3. At 3, I ask the same question, which activities end here? only one activity ends here. Remember, these two activities start from here. I am not on that. I am finding out which activity ends here. Which activity ends here? Activity B ends here. Okay. Activity B, what time it can start? 0. Activity B takes how many days? 4 days. So what time event number 3 will be reached, or activity B will be completed at the earliest? 0 plus 4. Not great calculation. Okay. Then I go to event number 4. Now the things become little different, little more difficult. What is the purpose? I am trying to find out the earliest time for event number 4. Which are the activities ending at event number 4? Which are the activities ending at event number 4? My question. There are 2 activities ending at event number 4. And what are their names? C and D. Both end at event number 4. And unless and until both activities are completed in all respects, event number 4 cannot be said to happen. Okay. So now let me see, since event number 4 depends on the completion of 2 activities, namely C and D, or 2-4 and 3-4. Let me see, 2-4, when will it end? This event happens at time 6 at the earliest. This activity takes 3 days. So 6 plus 3, 9. One answer which I get is 9. Okay. That means activity C will be over by time 9. But activity D also has to be over before event number 4 can happen. And when will activity D be complete? 4 plus 8, that is 12. And since both these activities are required to be completed for event number 4 to happen, I must take higher between the two, that is 12. So, in other words, event number 4 cannot happen before time 12. Okay. I have done the calculations at event number 4. So now I go to event number 5. Event number 5 is here. My question is same. Which activities end here? 2 activities end at event number 5. Which are the activities ending at event number 5? F and E. Okay. Let me see when E is getting completed. 4 plus 14, 18. Activity E will be completed earliest at the time 18. But not only activity E, activity F also has to be completed before this event can happen. When will activity F be complete? 12 plus 8, 20. Take longer between the two, that is 20. That means event can happen earliest at time 20. Do you remember we had found out 3 paths from the first event, A, C, F, B, D, F and B, E. You remember we had said that the longest path is 20, and this is the confirmation here that this event can happen earliest at time 20. And what is happening of event number 5? Happening of event number 5 is nothing but completion of the project, because 5 is the last event. When event number 5 happens, the project stands completed. Okay. Now what? The calculation of the network diagram is over to about half the extent. I have come to the conclusion one thing, that this project cannot be done before the end of 20 days. This will take 20 days. Do you remember the longest path was also 20? And what was the longest path? BDF, 4 plus 8 plus 8, 20. This is a better way, the foolproof way. Here you cannot make a mistake. If you try to find out various paths, you may miss out on some path, in which case your calculations may not necessarily be correct. But here, since we are going through each and every event and doing the calculations at the respective events, our calculations are definitely going to be correct. So event 5 happens at time 20. That means this project can be completed at time 20. So what next? Project can be completed in time 20. All activities are over. Yes. So what can be completed in 20 days must be completed in 20 days. Why should it take 21 days or for 22 days? So when I reach the last event, I only calculate the earliest time like this. And since my objective is to complete the project at the earliest, I will say that the latest time for the project is also 20 days, because it can be done in 20 days. It should be done in 20 days. Okay. So in other words, when I reach the last event, I only calculate the earliest time, and copy the same time as latest time. Remember this. If there are 10 events, I go through the process of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The moment I reach event 10, I only calculate the earliest time, and the moment I calculate the earliest time, I'll copy the same time as latest time. Okay. So at the last event, therefore, the earliest and latest time will always be same. Okay. Then the process of forward pass is over because I have reached the last event. The moment the process for forward pass is over, I commence the process of backward pass now. In the backward pass, what do? We go in the decreasing number of events. 5 is the highest number. So 5, 4, 3, 2, 1. That is how we'll go in the reverse sequence, backward pass. Okay. From 5, I go to 4. Okay. I come here. From 5, I go to 4. My question is here. 4 is here. My question is, from 5, I go to 4. My question is this: which activities start from here? Now see which activities start from here at event 4. Only one activity starts from event 4. Two activities end at event 4. That is 2, 4 and 3, 4, or C and D. But only one activity starts from event number 4. Now look at this event number 4 and particularly the activity 4, 5. What we understand is activity 4, 5 must be completed latest by time 20, and it takes 8 days for completion. So when should it start at the latest? 20 minus 8, that is 12. In other words, event number 4 must happen before time 12. It cannot happen before time 12, and it should not happen after time 12. But if it happens after time 12, suppose it happens at time 13, what will happen is 13 plus 8, this will become 21. That means the project will be delayed. So without delaying the project, when can latest the event number 4 must happen? It must happen by time 12. Okay. At 4, the calculations are done. So I am going to event 3. Remember, 5, 4, now 3. At 3, I ask a question. Usual question. Which activities start from here? There are two activities which start from event number 3. Remember, event number 3 here is such that one activity ends here, two activities start from here. One activity ends here, but two activities start from here. And what is the position here? One activity starts from here, but two activities end here. That is the difference between these two events. Now I have an event where two activities start and one activity ends. So I am on what? I am right now on this. Which activities start from here? So which are the activities starting from event number 3? 3, 4 and 3, 5, or D and E. Okay. I'll examine both. Okay. Now first I examine E. E tells me that activity E has to be completed by time 20, and E takes 14 days for completion, and therefore according to activity E, this event must happen latest by 20 minus 14, that is 6. Activity E tells me that event number 3 must happen by time 6. Now look at 3, 4, another activity starting from event 3. I am looking at both the activities starting from event 3. This is another activity starting from event 3. This activity D tells me that D must be completed by time 12, and D is going to take 8 days. Therefore this event must happen latest by 12 minus 8, that is 4. So one activity tells me that event must happen by time 6. Another activity tells me that the event must happen by time 4, and therefore lower between the two will prevail at event number 3. Therefore what we find is event number 3 also the earliest and latest time is going to be same, and that is 4, 4. I go to event number 2. Having done the calculations at event 3, I go to event number 2. My question is same. Which activities start from here? At event 2, if you see, the only activity which starts from event 2 is C, or 2, 4. C can be also called as 2, 4 because C joins 2 with 4. activity C must be completed latest by time 12 because event 4 can happen latest by time 12. Activity C takes 3 days. So according to activity C, this event must happen latest by time 12 minus 3, that is 9. And remember, there is only one activity starting from event 2. There is no other activity starting from event 2. Otherwise, I would have had to do another calculation as well. But since only one activity starts from event 2, that activity C or 2-4 tells me that event number 2 must happen latest by time 9. Now look at this. Look at this event. This is event number 2 I am drawing separately. This is 6 and this is 9. What does this mean? This means that event number 2 cannot happen before time 6 because this is the earliest time for the event and this is the latest time for the event. Therefore, it should not happen after time 9. It cannot happen before time 6 and it should not happen after time 9. That means, can you see that there is some kind of freedom or flexibility associated with this event number 2, and this event 2 cannot happen before 6 and should not happen after 9. That means 6 to 9, whether it is 6, 7, 8, 9, it is all right. This event can happen any time between 6 and 9, which means that there is some kind of freedom or flexibility associated with event number 2. The flexibility associated with an event is called as a slack. Remember the term I am introducing. Again, I have mentioned it earlier, but now I am introducing the definition of slack. Therefore, what is the slack? Slack is nothing but difference between the earliest time and the latest time. Sorry, the latest time minus the earliest time for an event is called as a slack. So what is the slack over here? Slack here is 0. Slack here is 0. Slack here is 0. But slack here is 3. Okay, so the only event so far which has got a slack is event 2 and the slack is equal to 3. 9 minus 6. Okay, I have done the calculation, almost completed. I am coming to event number 1. At event number 1, my question remains same. Which activities start from this event? Which are the activities starting from event number 1? 1, 2 and 1, 3 or A and B. When there are more than one activity starting from an event, do both the calculations and pick up the lower of the two numbers. Now look at this. 1, 3. Event 3 must be reached latest by time 4 and activity B takes 4 days. Therefore, according to activity B, event number 1 must happen latest by time 4 minus 4, that is 0. And according to activity A, event number 1 must happen by latest by time 9 minus 6, that is 3, and therefore it has to be 0 in the backward pass. So in the forward pass we pick up larger the numbers and in backward pass we pick up smaller the numbers. And one important thing now, if you do the calculations correctly at event 1, you will always find 0, 0 at event 1. So there are two events definitely in any network diagram. The first and the last event. At the first event, the two times will be always 0, 0. The earliest time for event 1 will be 0. Latest time for event 1 will be 0. And at the last event also, the earliest time and the latest time will be same. Over here in this problem, it is 20. Okay. So this way we have done the calculations in respect of this network. Now, let me analyze some of these activities of this network. Okay. Now see, there are 6 activities here. Some activities are critical, some activities are not critical. Which are critical activities I am trying to find out. Forward pass, backward pass process we have understood. We'll be repeating this n number of times in this video lecture. So this concept of forward pass, backward pass is going to become very, very clear for you and it will come automatically. The moment you start looking at a network, you'll start doing the calculations soon. Wait for some time. Okay, now look at this. I am taking up activity 3, 5. 3, 5. What is the name of the activity? Alphabetical name of the activity is E. What are the times at event 3, 4 and 4, and events at time 5 are 20 and 20. And what is the duration of E? It is 14 days. Okay. Look at this activity separately, not as a part of this network. Look at this activity separately. Let's see. Can you see that event 3 is joining event 5, and that is my activity E going from the direction 3 to 5. Always it has to be a forward direction. Activity such as 5, 4 is not allowed in any network. That means the numbering of events is wrong. It can be 4, 5. It can be 1, 9. Yes, 1 is smaller than 9. Activity is possible to have 1, 9. But no activity is possible to have such as 9, 6. 9 cannot join 6. 6 cannot be at the head of the arrow. Okay, fine. So, now look at this activity. This activity tells me that this activity, whatever it is, it must be completed by the latest time of this event, which is 20. That means this activity end time is 20. Okay. Now start time. Start time is the earliest time for this event. When can this event number 3 happen at the earliest? 4. So what is the time available? Between 4 to 20, this is the time available for completion of the activity. So I'll say time available is equal to 20 minus 4, that is 16. The total time available for completion of this activity is 16, whereas the activity takes how much time? It takes only 14 days. Which means that instead of taking 14 days, if this activity had taken 15 days, or for that matter 16 days, no damage would have been done. Even then, the event number 5 would have still happened at time 20. So this difference between 16 and 14, 16 is time available, 14 is time actually taken, is representing some kind of freedom or flexibility associated with activity called as E. And how much is that freedom or flexibility? Time available is 16. Time taken is equal to 14. Therefore, flexibility is equal to time available minus time taken, that is 16 minus 14, that is 2. The flexibility available in respect of activity E is 2 days. That means because of some reason or the other, suppose the activity E is delayed, how much can it be delayed? It can be delayed maximum by 2 days, and this 2 days is therefore total float for activity E. Okay, total float for activity E. Obviously, for a critical activity, the float is 0. The activity must be completed within the allotted time, otherwise the project will be delayed. Okay, now let's calculate. So we have understood that activity E has some kind of freedom or flexibility, and that freedom or flexibility is to the extent of 2 days. I'll introduce the mathematical formula a little later, but I'm just trying to understand which activities have some freedom, which activities do not have some freedom. Now look at activity A. I'm drawing activity A. A is here. The duration of A is 6 days. This is event number 1. This is event number 2. The times are 0, 0 here and 6, 9 here. Okay. I'm trying to find out how much float is available in respect of activity A. When should activity A be completed latest? Latest time for this event being 9, activity A must get completed before time 9, and it cannot start before time 0. Therefore, this 9 minus this 0 is time available is equal to 9, and time actually taken is 6 days. Therefore, the difference between the two, time available minus time taken, being 3 days, the total float or freedom or flexibility or the amount of time by which the activity can be delayed is 3 days. What it means is, even if instead of taking 6 days, if this activity starts taking 9 days, even then my project will be completed in 20 days. This activity, instead of taking 14 days, if it starts taking 16 days, even then no damage is done, my project will still be completed by time 20. Now this gives me some important information. Now I will come to know this way, if I do all the activities analysis, I'll come to know that certain activities can be delayed comfortably without affecting the project duration. And therefore, it gives me lot of freedom or flexibility in respect of implementing the overall project. Okay. Now, for example, suppose there are some activities which cannot be delayed. Now, let me see which activity cannot be delayed. Let's look at activity 3-4 here. Okay. I am drawing 3-4. This is 4. This is 3. What is the activity name 3-4? It is called as D, and it has a duration of 8 days. What are the numbers at event 3? 4, 4. Events at number 4 are 12, 12. Okay. How much time is available for completion of this activity? This 12 minus this 4. This is when the event number 4 must happen. This is when the event number 3 cannot happen before this time. So 12 minus 8, time available for this activity is 8 days, 12 minus 4, and the time actually taken by this activity is also 8 days. That means this activity takes the entire time available for completion of this activity. 8 days are available, 8 days are taken. That means this activity, even if it is delayed by 1 day, my project implementation will be delayed by 1 day. 20 will become 21. Instead of taking 8 days, if this activity starts taking 9 days, immediately my 20 will become 21. Whereas this activity can be delayed by 2 days. This activity can be delayed by 3 days. No damage done. But if this activity is delayed by even 1 day, my project will go beyond the schedule by 1 day. That means activity 3-4 is a critical activity. Done. Now let's calculate the remaining activities. This activity 2-4. 12 minus 6. 6 days are available for completion. Actually, it takes 3 days only. So there is a freedom or flexibility to the extent of 3 days. What about this activity? 4 minus 0, 4 days. Duration is also 4 days. Activity is critical. No freedom or flexibility. This activity, no freedom or flexibility. This activity, there is freedom or flexibility to the extent of 2 days. This activity has a freedom or flexibility to the extent of 3 days. This also has a freedom or flexibility of 3 days. And therefore, activity A, C and E, A, C and E, which have some kind of freedom or flexibility, they are non-critical. There is some delay which is possible. Activity A, for example, can be delayed to the extent of 3 days, or activity C can be delayed to the extent of 3 days, or activity E can be delayed to the extent of 2 days, and so on. There are certain activities which cannot be delayed, and those activities are B, D and F. Look at F. 20 minus 12 is 8. Time available 8, time taken 8. Activity is critical. So I'll mark the critical activities now by a double bar. 12 minus 4 is equal to 8. Activity is critical. 4 minus 0 is equal to 4. Activity is critical. Can you see this was the longest path which we had said? BDF. BDF, one path was 20 days, one path was 17 days, and one path was 18 days. Which path is 18 days? BE, 4 plus 14, 18 days. Non-critical path. Because of that one activity is critical, but this is not critical. On path ACF, F is critical, but A is not critical, C is not critical. In other words, out of A, B, C, D, E, F, A, C and E are not critical. And which are the critical activities? B, D and F are critical. So I am marking them B, D and F. These are critical activities. If you total up the durations of these activities B, D, F, it will be 4 plus 8 plus 8, that is 20. And this, there is no way to guess beforehand which are the critical activities unless and until you draw the network diagram. Now that we have drawn the network diagram systematically, we understand that activities B, D, F are critical and activities A, C, E are not critical. Therefore, there exists a possibility that if required, we can delay activities A, C and E, but we cannot delay activities B, D and F. So B, D, F critical activities, A, C, E non-critical activities. With this information, we'll try to hereafter take up some problems where there are larger networks, more events, more activities and more involved calculations. Okay, thank you.